Okay, this is probability review part one, and this is sample space, and this is video number two. And I know we referred to sample space a little bit in the first video. We're going to spend a little bit more time with it here. So the distribution of colors of candies, and by the way, the reason why is sample space can help you solve a lot of problems if you actually create one. The distribution of colors of candies in a bag is as follows. If two candies are randomly drawn from the bag with replacement, what's the probability that they are the same color? I'm going to tell you that's initially confusing, but it's like, well, what's the probability I get two brown? Well, that'd be a brown and a brown. Well, the probability of a brown is 0.1 times 0.1. Well, that's the probability of two browns. Well, I can do the same thing over and over again. Probability of a red and a red, which is going to be 0.15 times 0.15 plus, and the reason these are pluses, I'll get to in just a second. A yellow is going to be 0.2 times 0.2. A green is 0.25 times 0.2. Oops, this should be green here, and this should be 0.25. And really, I'm just going to tell you, as soon as I started writing down the possibilities, or the very first one, I go brown and a brown, is like, I can figure that out. As soon as I figured out that, it's like, oh, the rest of this falls into place for me. Now, there's a reason why these are pluses. I'm only drawing two candies. Well, if I'm drawing two candies, I can draw two browns, but I can't draw two browns and two reds at the same time. I'm only drawing two. So this is a brown and a brown, or maybe I draw a red and a red, or maybe a green and a green, or maybe a yellow and a yellow. And whenever it's an or, then I get to add them, all right? So this and this, or this and this. And please remember, and usually means multiply, or usually means add when we're working with probabilities. Now there's some restrictions on that, but in general, that's the case. So in this case, 0.1 squared plus 0.15 squared plus 0.2 squared plus 0.25 squared plus 0.3 squared. And that equals 0.225. All right. Okay, so that would be that one right there. The next thing, a weighted coin has the probability of 0.35. So this is probability of heads. If that's the probability of heads, probably need to note that the probability of tails equals 1 minus 0.35, which is 0.65. A game is played in which a person wins if they flip heads twice. So you get to flip heads twice. The coin will be flipped a maximum of 3 times, or someone wins whichever occurs first, okay? So create a sample space which provides all the possible outcomes for heads to win. Well, I could flip a heads, and I could flip a heads. Yep, I could do that. And I would stop flipping because I already win, so I wouldn't flip it a third time, because that's what they said. They said, or until someone wins. Well, I can do that. What happens if I flipped a heads first, followed by tails? Well, then I would need to flip it I get to flip it one more time. And if it's heads, I win. Alternatively, I could flip tails on the first flip, but then I'd have to flip 2 heads in a row in order to win. So those are the combinations of winning. Then it says, determine the likelihood that someone would win with heads. Be certain to show your work. Well, I'm going to refer back to this. The probability of flipping a heads was 0.35, so 0.35 squared. The probability of getting a heads, a tail, and a heads would be 0.35 times 0.65 times 0.35. And I could also win if I got a tail followed by 2 heads. Now, these are the ways I could win. So I can win this way, or I could win this way, or I can win this way. So I'm going to need to add these probabilities. All right. So it's going to be, in this case, essentially 0.35 squared plus 0.35 times 0.65 times 0.35. And I know there's different ways to show this, plus, but I'm going to show it with a way that I actually wrote it out. 0.65 times 0.35 times 0.35. And there you go. So the probability that I win would be 0.28175. Now, once again, the probability of two heads is 0.35 squared. So I could win this way, or I could win this way, or I can win this way. And like we said earlier, or typically means add. All right. So that was 2 and 3. I just showed 3 on the same one. Each of the faces of a 6-sided number cube is numbered with the numbers 1 through 6, with a different number appearing on each face. 2 number cubes will be tossed. Anytime I see 2, I'm pretty much sure I'm going to have to do a sample space of some sort or a table. We'll do tables in a later video. And the sum of the numbers appearing on the faces that land up will be recorded. What's the probability the sum will be less than or equal to 5? Well, first off, I'm going to let you know that if for this, I would highly recommend you do this 3 or 4 times the day before the test so that you get fast at it. So 1, 1, 1, 2, because I get a 1 on the first, 1 on the second, 1 on the first, 2 on the second. So these are my dice rolls. And by the way, this probably takes less than a minute or less than a minute and a half. So it's totally worth the time it takes to do this. Because if you do this, you're almost assured of getting it right, the problem right, because the only thing you have to worry about is careless error at that point. So you go ahead and set this up. So I'm making all my combinations, not that I want to, but I want to get the problem right. And even on multiple choice, it's certainly worth the time to do this. All right, I've pretty much ran out of things to ramble and say. So I'm going to keep working on this writing and filling dead space with my voice. Okay, so what is the probability the sum will be less than or equal to 5 given the sum is less than or equal to 9? So less than or equal to 9, that is all of these. Okay, so I can count all of those up. And first off, and so there are 36 possibilities. And 1, 2, 3, 4, 5, 6. So 36 minus 6 is 30. So basically, if I counted this up, 1, 2, 3, all these up, they should sum up to 30. And remember, given is in the denominator, the intersection's in the numerator. So I had 30 possibilities in the denominator. And it says less than or equal to 5. Well, my less than or equal to 5 is this group right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case, 10 out of 30 equals 1/3 or equals 0.333. All right. So once again, take the time, make a sample space when you're rolling the dice. Yes, it takes some time, but it'll get you a problem right, and and you have enough time to do it. You can definitely do that problem in less than 2 minutes. This is one of the more difficult sample space problems, but once again, if you will set the sample space up, you're going to get it right. So the probability of a point obtained in one game is independent of the number of points obtained in a second game. So they're telling us they're independent, which means we can multiply. That's the key point of that. And the game is played twice, and here's my key. It says, oh, it's being played twice. As soon as we're doing something twice, we probably need to make a sample space. the sum of the number of the points could be 0, 1, 2, 3, or 4. If y represents a sampling distribution of the game, for which value of y will the probability be the greatest? So here we go. First off, we're going to set up a sample space. So on the first game, I could get 0 points, and I could get 0 points on the second game. And I could get 0 on the first, 1 on the second, 0 on the first, 2 on the second. I could get 1 on the first, 0 on the second, 1 on the first, 1 on the second, 1 on the first, 2 on the second. And then the last one, I could get 2 on the first, none on the second, 2 on the first, 1 on the second, 2 on the first, and 2 on the second. Now, 0 plus 0 sums to 0. And it's like, oh, yeah, I could get 0. But to get that, to get this, I have to get a 0, 0. All right, that will get me 0 points. To get me 1 point, that gets me 1 point, which is going to be a 0, 1 or a 1, 0. To get 2 points, that's these three, which is 0, 2, 1, 1, or 2, 0, 3, 1, 2, and then a 2, 1, and a 4, I have to get a 2, 2. All right. So the probability of getting a 0 and a 0, that's going to be 0.5 times 0.5. So this is 0.25. The probability of getting a 1 is going to be 0.5 times 0.3. Or, because I can either do it this way or I can do it this way, so I have to add these, 0.3 times 0.5. Well, that's going to be 0.15 and 0.15. So this is 0.30. Make sure I did that right because it's early in the morning. Good. Okay, I can get a 0 and a 0 and a 2. A 0 is 0.5 and a 2 is 0.2 plus the 1 and a 1 is a 0.3 times 0.3 or 0.3 squared plus a 0.2 times 0.5. So 0.2, or excuse me, 0.5 times 0.2 plus 0.3 squared plus 0.2 times 0.5 is 0.29. And here I can get a 1, 2, or 2, 1. So this is going to be 0.3 times 0.2, and this is plus 0.2 times 0.3. And always do check your math because see, it's easy for people to go, oh, that's 0.6, and no, it's 0.06. So 0.06 plus 0.06 is 0.12. And this one is going to be 0.2 times 0.2, which is 0.04. All right, when we look at that, this one is the largest. So the answer to the question, which of these, when the game is played, for which value of y will the probability be greatest? And the probability will be greatest for getting 1 point. So basically what they're saying is your best, if you play the game twice, the most likely thing that will happen is that you get 1 point. Now, the other thing is, it should be a valid probability distribution, so I should be able to check myself. And if that's the case, I should be able to go 0.25 plus 0.30 plus 0.29 plus 0.12 plus 0.04 should equal 1 if I did my math correctly. All right. Okay, this concludes this video, the sample space video. Thank you.